Welcome back for part 3 of a discussion of Diophantine equations. So far, we started with the equation a plus b equals c, and we said, hey, let's find some positive integer solutions to this equation. Obviously, there are infinitely many solutions, and we began changing the equation in very small ways to make the problem more difficult. So at the beginning, we just said a plus b equals c. We didn't have any conditions on a, b, and c. We said let's make them positive integers. We discussed changing the operation, and we discussed adding exponents. When we got to the a squared plus b squared equals c squared version, solutions to that are Pythagorean triples, and we had a discussion about how to calculate the primitive triples and how to calculate triples in general. We know how to construct not just some solutions to that equation, we can construct every possible Pythagorean triple in a very organized manner. There's an algorithm that will definitely construct any triple that we want to construct by the correct input yields the output that we want. If we didn't have that algorithm, or if we didn't know about the algorithm and we wanted to construct solutions, we could use brute force. So to use brute force, this would mean trying everything until we found the solution that we're looking for. So if we wanted to find all the solutions up to a specific point, we could just try every possible value. And if something is a solution, record that. And if it's not a solution, go on to the next thing. With brute force, this only works when there are a limited number of possibilities. It can be a very large number, but it needs to be a limited number of possibilities to examine. And we need to make sure that we are checking everything. If we leave out any one possibility in our check, then we haven't brute force. That may have been an answer, it may not have been an answer. By not checking it, we have lost some of the information. So brute force, we have to be very careful to make sure that we are checking everything. But even when we're checking everything, if we're looking for solutions, if we're looking for, say, the very first potential solution, the order that we do the checking might have an effect, how we do the checking, and so on, can change the amount of time that it takes to find the solution that we're looking for. But brute force is basically trial and error, and you just keep trying everything until you find a solution of the form that you want. So in a Python way, we could start off with an empty list. I called it PT for Pythagorean triple, keeping it short. And in the equation, we have a squared plus b squared equals c squared, so we could just loop through values for a, for b, and for c. So let's say we wanted to just look for the values where a is from 1 to 99. We could loop for a in range 1 to 100. Then we could loop through the values for b, and also from 1 to 100, and c from 1 to 100. And then just check to see if a squared plus b squared is equal to c squared. If a squared plus b squared is equal to c squared, then we could just append that triple to our list of triples. So that is a way to brute force through all possible values of a, b, and c. Now notice that there are some things happening here with different values being checked that don't necessarily need to be checked. So we could improve on this a little bit. We also might potentially benefit from changing the order of our calculations, looping instead of the ABC order, maybe looping in a different order. And so the idea is just because we're brute forcing to find solutions doesn't necessarily mean that all versions of brute force are created equally. We might be trying a bunch of things that are guaranteed not to give a solution, or we might be trying the same answers again or the same things again in a different order. And so we want to, generally with brute force, think about it a little more carefully and make sure that we are checking everything exactly once in a nice way. But even if we don't do that, we can still apply brute force and find solutions sometimes to situations. And in the case of these Pythagorean triples, we would be able to find solutions. Now, something we could do, because of repeating values, if A, say, we're already up to 50, and B is supposed to be, in our Pythagorean triple order, we had A less than or equal to B, and then C was the largest value. Instead of looping B from 1 to 100 when we got there, we could loop B from A to 100. So whatever A that we're on, then start there when we're looking for the B value. Don't start all the way back at 1. Again, because we're going to be going back to duplicate some things that we've already done. And so we could change, again, some things about the loops themselves. So here we change the range of the loop. We could change the order of the loops. And then if we thought of this, we're looking for a solution rather than trying to create all the solutions, what if we put this process into a function and return as soon as we get the first valid triple? So rather than appending to a list somewhere, what if we return as soon as we get a valid triple? We say, okay, this one works, return ABC. And so there definitely we can see that looking through things in one order might be more likely to find a solution sooner, whereas other orders might find solutions later. Okay, so with brute force, the idea is we want to see all the possibilities, at least all the possibilities until we find an answer. But there can be benefit to a particular order or a particular way of doing things that will give us the solutions that we're looking for sooner rather than later. All right, so with our equation a squared plus b squared equals c squared now, let's consider some other incremental changes that we could do. Another thing that we could do is we had the exponent was 1 in every case, then we made the exponents all 2, or we worked our way up to that and got the exponents all to 2. What if we just made all of the exponents 3? So now we're trying to find a solution in positive integers to the equation a cubed plus b cubed equals c cubed. Now at this point we don't know a formula, we don't know a procedure to calculate these, and so we could use our brute force code to look for solutions to this equation. And so we look back at the brute force code that we just created and think about what we would have to change to make that apply to this particular equation. We could say, what would the code look like? What ranges should we consider? Since we don't know how many times we're going to do this, rather than having a counted loop the way we do with the counted for loop, should we consider a way to use a while loop? Because a while loop can be this unknown number of repetitions. And so there's some things we could think about, but let's think about what the minimum change we would have to make to our code to look for solutions to this a to the third plus b to the third equals c to the third. And so pause the video, take some time, modify the code, and see what you can find out in terms of a solution to this equation, a to the third plus b to the third equals c to the third. As you are doing that, you might think about how long should you let your program run when you're looking for solutions. So what range should you look at? Expand the range if you don't find solutions. How long should you let it run? And be reasonable in terms of how much time you have available to think about how much time you want to let this program look for solutions. So go ahead and pause the video and see what kind of solutions you can come up with. All right, I hope you didn't spend too much time with that, because we want to talk about a famous problem called Fermat's last theorem. So Pierre de Fermat was a French lawyer and mathematician, lived in the early to middle parts, or I guess into the later part, to 1665 of the 17th century. And Fermat was, again, a lawyer and a mathematician. He worked in areas of analytic geometry. He worked on an early version of differential calculus that both Newton and Leibniz were aware of and helped them and develop. His work helped them develop calculus in the ways that they did things. He did foundational work in number theory and probability and in physics. In studying number theory, he had a copy of Diophantus's Arithmetica, and around 1637 he made a note in his copy of the book to the effect that the equation a to the n plus b to the n equals c to the n has no positive integer solutions when n is greater than 2. And then he went on to say that he had a wonderful proof for this fact, but the margin of the book was too small to hold to contain the proof. Well, he never went back to prove it. He didn't share it with other people. It was found in his books after he had died, and no one knew whether his statement was true or not. It was called Fermat's last theorem because his other work was either proved or disproved over time, and this was the last one that people didn't know the solution to. Now let's think about what would happen if this statement is true. Then that means our efforts that we just made in looking for a solution to a to the third plus b to the third equals c to the third would be to no avail, because there are no positive integer solutions if Fermat's statement is correct. Well, people tried and tried and tried for years and years and years, hundreds of years, to solve this. Someone would come up with a proof, and people would find errors in the proof, keep trying things, and there's an error, there's an error, there's an error. And in 1994, a British mathematician who was at Princeton at the time, Sir Andrew Wiles, presented a proof of a much more general statement, but one of the corollaries of that statement was Fermat's last theorem. So everyone thought, wow, this is exciting, this is great. He's proved Fermat's last theorem finally after 350 some years, 356 years or so. He has proved this statement. Well, as people then started to analyze, once again, there was an error in that proof, and people started thinking, okay, well, once again, there's a mistake, and this wasn't a proof. But Wiles and his student Richard Taylor spent some time, a lot of time, worked really hard, reduced the length of the proof considerably, and fixed the problem. So finally in 1995 they were able to present, yes, here's the final correct proof of Fermat's last theorem. So now we know for sure that an equation of the form a to the third plus b to the third equals c to the third has no integer solutions, in positive integer solutions. And so you keep raising the exponent, and now we can't solve those equations. So we start off with a plus b equals c. We have a squared plus b squared equals c squared has lots of solutions. You can put different exponents on things and be able to get solutions, but if you have all the exponents being the same and larger than 2, then there are no solutions. Now, the mathematics that Wiles needed to prove this was well beyond anything that Fermat could ever have known. The ideas didn't even exist until the 20th century, and so no one has ever found a proof that would match something that Fermat may have thought. Did he have a proof? Most people think he probably didn't. He probably made one of the same kinds of mistakes that people did over the next 350 years. Okay, so what happened was we went from a plus b equals c, made very minor modifications, and very quickly got into problems that are research level, and then problems that are completely unsolvable. So let's go in a new direction. Let's change the exponents. Let's have a mixture where we have a to the third plus b to the fourth equals c to the fifth. Is that more difficult? Is that easier? What happens? In this situation, I will tell you going in that this equation does have positive integer solutions. So we aren't in the a to the third plus b to the third equals c to the third scenario now. We do have an equation that does have solutions. And so notice I said solutions plural. So what I would like for you to do is to see how many you can find. Can you find one solution? Can you find two solutions? Remember, a solution consists of all three values. It's a triple, A, B, C. So can you find a solution to this equation? If you can find one, can you find more than one? You can look at the brute force Pythagorean triples code that we just put together, modify that, see if you can make it work. Again, the same kinds of questions. What kinds of values do we need? How far do we need to check? What do we need to look for? What's the appropriate order for looking at the values? What can we do to make sure that we're brute forcing our way, but in the most efficient way with that brute force process? And so let's go through and see what we can find out in terms of finding a solution to this equation. Again, pause the video, take some time, see if you can find a solution. All right, so in terms of finding solutions, the brute force method will work so long as we look far enough. If we allow the values to be big enough in our range, we will eventually come up on a solution. But I want to look at this from a mathematical perspective to help give us some guidance on looking for the second solution beyond that, or for other solutions potentially. So if you remember things about exponents, you will remember that 2 to the n plus 2 to the n is equal to 2 to the n plus 1. You can factor out a 2 to the n from each of those, and you're left with 1 plus 1. So 2 to the n times 2, and that's just 2 to the n plus 1. And so we want to make this kind of structure, we want to see if we can make this match our equation of a to the third plus b to the fourth equals c to the fifth. And so the idea is we want to write a as 2 to a power, b as 2 to a power, and c as 2 to a power. So like 2 to the r plus, and 2 to the s and 2 to the t. But we then want the a to then be raised to the third power, and b to be raised to the fourth power, and c to be raised to the fifth power. So the idea there is that making this match the 2 to the n plus 2 to the n equals 2 to the n plus 1 situation, we would need the 2 to the r to the third, which is 2 to the 3r, to be the same as 2 to the s to the fourth, which is 2 to the 4s. So 3r has to equal 4s because these two values are the same. And then one more than that is the 2 to the t to the fifth, or 2 to the 5t power. Okay, so there's some algebra in there that is allowing us to match the a to the third plus b to the fourth equals c to the fifth equation with the structure of 2 to the n plus 2 to the n equals 2 to the n plus 1. And so we're looking for a solution of r, s, and t that will work. And so as a hint, let's see if n is 24, what happens. So again, pause the video for a moment and see if you can figure out what the r, the s, and the t need to be in order for these values with 3r, 4s, and 3r plus 1, or the 5t, to match the structure up here. All right, so if we solve for r, s, and t in these situations, then we have 2 to the 8th raised to the 3rd power plus 2 to the 6th raised to the 4th power equals 2 to the 5th raised to the 5th power. So hopefully your code gave you solutions of a being 2 to the 8th, and b being 2 to the 6th, and c being 2 to the 5th. Now again, your Python code would have given that to you as actual integer values, so you can check to make sure that we got the same answers as your first solution. So now we have a solution to the equation. Can we find more solutions to the equation? Turns out there are infinitely many solutions to this equation, so this is much better than the a to the third plus b to the third equals c to the third scenario. All right, so you want to think about how to find other things. N equals 24 gives us a solution. What if we pick a different value of n? Not every value of n will work, but there are choices of n that will give you solutions. And once you find your next choice of n, then the choice of n after that, and the choice of n after that, hopefully you will see a pattern that allows you to find infinitely many solutions. Now, we can't find infinitely many solutions with code, but we can confirm a solution. Once we think that something is a solution, we can confirm that with the code. Again, as long as these numbers don't get too big. If the numbers do get too big, then we can confirm this mathematically, that this thing works as a solution, or no, this one does not work as a solution. All right, so what you want to try to do is you want to think about what a general pattern might look like for these solutions. This structure here with the 3r, the 4s, and the 5t is still going to need to carry over. What values of n work? So what are the actual r, s, and t values that will work in terms of finding a solution? So this will give us all these solutions that involve 2 to a power, and all the three values a, b, and c are all these even values that are 2 to a power. Change your code, your brute force code, look for larger values, and see if you can find solutions that do not involve powers of 2. See if you can find solutions that involve some other values. Maybe you have odd numbers involved. Maybe you have some even numbers and some odd numbers. See what you can do about finding other solutions to the equation. There are lots and lots and lots of solutions to this particular equation, but again, not every number will work. All right, so Fermat also, again, did lots and lots of work in different areas, but some other number-related Fermat problems, things that he looked at. Something called Fermat numbers. I don't think that he was egotistical enough necessarily to name them after himself, but these were named after him later. And these are numbers of the form 2 to the 2 to the nth plus 1. So n's a non-negative integer. It could be 0, but it can't be negative. And we're looking at 2 raised to a power where the power itself is a power of 2. And then once we have that number, we add 1 to it. So if we let n be 0, remember that 2 to the 0th power is 1. So what we're looking at is 2 to the first power plus 1. Well, that's 3. And so when n is 0, the corresponding Fermat number is 3. You can check to see what happens when n is 1. The corresponding number is 5. When n is 2, we're up to 17. You can keep trying larger values of n. And the first question that Fermat asked at the time was, well, we have these numbers 3, 5, 17. And he calculated some more values, and he asked the question, are all these numbers prime numbers? So take some time, see if you can answer that question. We're not going to answer it now. You can take some time and some effort and see, are all the Fermat numbers prime? And if so, by test, everything you test as prime still doesn't mean that everything is prime. There's some more thinking to do. But if you were to find a Fermat number that's not prime, then that would be a clear answer that the answer is no, because as soon as we find a single counterexample, then the answer to the question is no, they're not all prime. Another area where Fermat worked was in a set of equations called Pell's equations. And we'll see more about these later on. But Pell's equations, there are positive Pell's equation and the negative Pell equation. By the way, as this is the case in a lot of scenarios, Pell's equations are named after someone named Pell, but they should have been named after someone else. But that's the typical way things happen with naming. The person who made something famous or the person who brought something to the attention of a famous person often gets things named after them. Not in a malicious, it's not malicious way of doing things. They're not intentionally cutting someone else out. It's just that people don't always know where the history of how something developed, and so it gets named after a famous person. So in this situation, we're looking for positive integer solutions to equations x squared minus dy squared equals 1. And then d can take on different values, and so with d taking on different values, we're looking for these solutions. And d itself can be positive or negative, but the structure has the x squared minus dy squared equals 1. You could pick some specific values, put a 2 in there, put a 3 in there, and see if you can find solutions to an equation like this. Fermat asked different mathematical colleagues to solve this equation for d equals 61. He had found a method to solve these equations. Other people didn't know this process. And so it's kind of an intellectual challenge. Hey, can you solve this equation? If you don't know the process, this is a very difficult thing to do in the mid-1600s. If you do know the process, then you have access to like higher level tools, and so that makes you a better calculator, right? You're able to solve more kinds of problems. The negative version of the equation, it looks exactly the same, x squared minus dy squared, except it's equal to -1. And so you could say, well, let's do the same thing. If you found a solution to x squared minus 3y squared equals +1, can you find a solution when the right-hand side is -1? And again, this is an aside from where we want to go, but it's interesting to try to solve these kinds of equations and see what you can find out. What can your code do? What can you modify with your code? At what point does just trying things no longer work or is no longer beneficial for us? When do we need a better idea? When do we need a longer runtime, right? So it's one, sometimes it's the other. We just need to let it run a little bit further, or maybe there's something more detailed that we need to do. We need to really change the focus and think about it in a different way. We need to change the order of things, or we need completely new tools to tackle a particular problem. All right, so another problem that we could look at that's a similar kind of Diophantine scenario. This particular one is from a book called The Canterbury Puzzles and Other Curious Problems. This is a book that was originally published in 1907. My version is the second edition from 1919. And the general theme is we have a collection of stories that didn't make it into Chaucer's Canterbury Tales. So you have the same kind of characters who are on this pilgrimage, and rather than telling the stories that made it into the Canterbury Tales, they're sharing puzzles. And so this book shares those kinds of stories, and they're really brain teasers that he created or developed or found over the years. And a broad variety, some very simple, some very wordplay orientated, some are various twists, some are based on images that are presented in the book, some are more involved mathematical problems. And one of those problems is a story about a dinner party, and one of the attendees places 3 empty teacups on a table and challenges anyone to place a total of 10 lumps of sugar into the teacups so that there are an odd number of lumps in every cup. So the first task is figuring out how to solve the problem. One of the characters in the story says, oh, I can prove that it's impossible. I'm a student at Oxford University. I'm studying law. I know logic. I know how to think about problems like this. You can't do this because if you add 3 odd numbers together, you always get an odd number. And since we have to use all 10 lumps of sugar and exactly those 10, that's part of the details in the story, these exact 10 lumps of sugar. You have to use all of them. They all have to go into a cup. And so he says, oh, you can't solve this. And then, of course, there is a solution to the problem if you think about it very, very carefully. So how do we solve her problem? This is a problem that is a Diophantine equation. We have how many are in the first cup plus how many in the second cup plus how many in the third cup. A plus B plus C is 10, but we have then this situation that we need the amount in every cup to be an odd number. So we have to really think about that. I may have said something that doesn't quite fit with the storyline. We have to think very carefully about how to turn the English into the appropriate mathematics. So take some time, think about how to solve that problem, and then once you figure out how to solve that problem, the question that would be a computational kind of problem is how many different solutions are there? So later on, come back to this problem, think about it, how do you solve this, and then once we have a solution, can we build more solutions? So the first part of the thinking is thinking without the computer, probably counting solutions. Once we know what a solution looks like, then we can possibly using brute force, write code that will allow us to find all the different solutions to this problem. And of course, once we answer this for 10, the idea is, well, what if we wanted 12 or 42 or 68 lumps of sugar? What if we wanted to find out how many solutions there are for other even numbers of lumps of sugar? Odd numbers of lumps of sugar, the problem is easy. It's not interesting at all. It's only when we make the number of lumps an even number that we get a challenge. All right, another problem that we could look at that's related to this is a problem of lucky numbers. Now, I'm using this term lucky numbers because of one particular author that used this. If you look up lucky numbers on Wikipedia or something, this is not the definition that we're looking at. So this term is not the standard name. The lucky numbers is usually used for something else. But in this particular case, we're going to just agree that we're calling a positive integer lucky if it can be written as the sum of positive integers whose reciprocals sum to 1. So to make a little more sense out of this, let's look at an example. 1 we're going to say is lucky by default. It's not really the sum of positive integers, but its reciprocal is 1. So 1 we're just going to agree 1 is lucky. But if we look at 2 and 3, 2 and 3 are unlucky because the only way to write 2 is either as 2 by itself or as 1 plus 1. And so 2 by itself, its reciprocal is 1/2. That's not 1. And 1 plus 1, when we look at those two values, 1 over 1 plus 1 over 1, well, that's 2. And that's also not a reciprocal summing to 1. So 2's unlucky. 3, for the same reason, is unlucky. You can check all the possibilities. Okay, 3 by itself, 2 plus 1, 1 plus 1 plus 1, none of those work. But it turns out that 4 does work. There are lots of ways to write 4 that don't work for us, but 4 is equal to 2 plus 2, and 1/2 plus 1/2 is 1, so 4 is a lucky number. So you can start trying other values to see, is this value lucky, is it not lucky? And so the challenge, the task then, is to describe all the lucky numbers. If a number is not lucky, we call it unlucky. And so the same kind of idea is, can we describe the unlucky numbers, right? What makes a number lucky? What makes it unlucky? How many of each are there? And so these are the kinds of problems that we are interested in. All right, so as usual, feel free to ask questions in the comments, by email, or on Discord, and have a great day.